The latest version of ProtoTwin includes many significant features and upgrades to the software. This video is quite a long one, but hopefully very exciting. So let's dive right in. We've added a brand new transmission component. This component can be used to relate two joints. The position of one joint can be related to the other through a given ratio. You can relate a prismatic joint to a path joint, a revolute joint to a path joint, a prismatic joint to a revolute joint, a prismatic to a prismatic, a revolute to a revolute, and finally a path joint to another path joint. This component is very powerful since it allows you to create complex relationships between joints in your ProtoTwin models. In this first example, I've already gone ahead and configured the joints. There is a path joint, a revolute joint, and a prismatic joint. I've also added a spring component to the prismatic joint, which applies stiffness and damping to the spring. I'll now go ahead and add a transmission component to the main entity. We need to specify both the input joint and the output joint. The relationship is defined as the output joint position is equal to the input joint position multiplied by the ratio. The second transmission component will be used to relate the last two joints so that all the joints are constrained to have equal positions. If we run the simulation, we can interact with the physics to test our model. The constraint is solved entirely by our physics engine as part of the overall system of constraint equations. Unlike other physics simulators that constrain only the velocities, the transmission component ensures that the positions of the joints do not drift apart over time. In this next example, I'll demonstrate how we can use the transmission component to simulate two simple gears. Here, the gear ratio is defined as the ratio between the number of teeth of the two gears. And that's all there is to it. One important thing to mention is that, with this approach, you no longer need to add physics colliders to the body of the specified entity. Since it is solved as part of the system of constraint equations, it makes simulating things like gears and rack and pinion mechanisms way more computationally efficient. We've also made a number of improvements to the Onshape importer. If you swap to the Onshape tab, there is now a search bar. You can use this to quickly search for a specific document if it's not high up in the list. You can also copy and paste a link to a particular document. This works with your own documents, but should also work with any public Onshape document. I'll now go ahead and import the main assembly for a simple robotic pick and stack model into ProtoTwin. All right, now that we've been able to transfer our CAD into the simulation environment, at this point you can start adding components to the specified entities. I've already gone ahead and configured the components. When you're ready, you can click play to start the simulation. What makes ProtoTwin useful is that you can use our tool to test your control logic and detect a variety of different issues with your design. It may be required that you make modifications to your design. In this example, everything seems to be working fine. But perhaps the stand for which the robot is mounted is placed too far down, so we should maybe move it up slightly in Onshape. All right, now that we have the document open in Onshape, we can start by making some modifications to the design. I said I wanted to move the robot up slightly, so I'll go ahead and use the transform tool to accomplish that. I now need to go and select all the parts of our X-Arm U-Factory robot that need to be transformed. I want to translate the robot by an XYZ vector. Let's move the robot up 10 centimeters. Maybe not enough. I'll try 15 centimeters instead. All right, that seems better. I'll now confirm the changes I just made. The changes in Onshape are now done. But the question now is, how can I quickly synchronize these changes back into ProtoTwin without starting again from scratch? If we come back into ProtoTwin, you will now see a sync button to the side of the import button for the main assembly. Clicking this button will enable ProtoTwin to re-import the CAD and then automatically reassign the components that you configured in ProtoTwin from your previous model into the next iteration of your model. Okay, cool. It appears that ProtoTwin has re-imported the CAD. Importantly, the stand to which the robot is mounted is definitely higher now than before. The real question now is, does the simulation still work? Okay, the robot has moved to the first target correctly, and it seems like all the robot's movements have updated correctly too, which is very promising. You may need to reselect some component properties after performing CAD sync, But generally, the changes you need to make to your ProtoTwin model will be minimal, as long as the changes to your design are minimal as well. ProtoTwin treats the CAD as the source of truth, and then just re-adds the components to whatever changes you made in the CAD software. Sometimes imported CAD may include some faulty topology. For example, sometimes disjoint meshes will be treated as a single entity with a single graphics mesh, which may be desirable or undesirable, depending on the circumstance. If you right-click on this entity in the Explorer, you should now see a Tools submenu option appear. If I click on the Split tool, doing so will open a new dialog window. I just need to click the Execute button to execute the Split tool. As you can see, this operation resulted in the creation of 4 different submeshes, with a new entity being created for each individual mesh. It is also possible to merge many different meshes into a single mesh, which is constructed as the union of all the separate submeshes. Once again, I need to open Tools and then click the Merge option. Doing this will create a new entity at the center of the bounding box of the merged entities. This operation can be particularly useful since reducing the number of entities in your ProtoTwin model can lead to improved performance when stepping the simulation, which is particularly important if you have a large number of vectorized environments when training machine learning models. It is also possible to create your own custom tools. In this next example, I've created some simple parts that I would like to move along some path with physics. I'll first go ahead and add a path component to the parent entity. I now need to specify the curve for the path. I can configure this using the feature selection, then by hovering over a feature of the mesh and clicking to confirm. I'll now go ahead and show you the tools I created, which should help speed up the process of configuring everything we need for the model to work. The Path tool is a class that extends the base class, tool, for all custom tools. The Path tool takes the entity as a generic type. For tools, it is also possible to specify properties, just like we saw with the Split tool earlier, which causes a dialog window to open. It is required that we must implement the valid function, which determines whether or not the tool should be displayed in the Explorer. We must also implement the execute method, which gets run whenever we click the execute button. In this case, for the Path tool, we first iterate over all the selected entities and then add a physics component to each one. We then add a path joint to that physics component and configure the path property we specified earlier to the path that was bound to the joint. And that's it for the Path tool. I've also created a transmission tool that does something similar to the Path tool. The transmission tool has a single property for the ratio that will be used to set up the transmission components for the parts along the path. For the execute function, we first sort the entities by name so that they appear in the correct order. We then iterate over all pairs of selected entities, retrieving the joint for each one, then proceed by adding a transmission component to the entity passed as an argument to the function. We configure the ratio, the input joint value, and the output joint value. And that's it for the transmission tool. In this way, with tools, you can programmatically modify ProtoTwin models, effectively automating away some of the tasks that may take a long time to configure through the GUI. I'll now go ahead and select all the red parts, for which we want to add the path joints. If we right-click in the Explorer again and open the Tools submenu, you should now see options for the Path tool and the Transmission tool that we created earlier. For the Path tool, remember that we need to specify the path property. For this, we'll choose the path component that we created at the beginning. Clicking the Execute button now, we'll call the Execute method of our Path tool, which should add a physics component and create a path joint for each of the parts we selected. If we swap over to Navigate mode, we can interact with the physics to test if our joints were set up correctly. Everything seems to be working fine, but what if we want to chain them together? Well, for that to work, we need to add a transmission component between each pair of parts. If we right-click on the parent entity, we can then execute the transmission tool, which should help accomplish this. If you recall our transmission tool, this will add a transmission component to the Part Studio for each pair of selected entities. We can check to see if this worked. by first selecting the Part Studio and then checking whether the transmission components were added correctly or not. Everything seems to be fine. If we run the simulation again, we can interact with the physics to check whether they are chained together correctly or not. This approach is pretty helpful, since it allows you to drive the parts around the path with a single motor. Instead of attaching a motor component to every single part entity and then driving each of them individually. Just like we saw in the previous example with custom tools applied to entities, it is also possible to create a custom tool applied to the world or a custom tool applied to a component. I've already created a move to floor tool and a duplicate tool, which will duplicate an entity along a particular axis. For the tool applied to the world, this tool iterates over all the descendants of the world, i.e. all entities, and then replaces all material instances with a different material. The component tool acts on a physics component and simply applies a force to the body's center of mass. I'll first select the main entity for the bipedal robot, and then use the gizmo to move the bipedal robot up slightly. If we run the simulation now, oh wait, he recovered, but oh no, haha, he just fell on his face. All right, maybe we should help him out a bit. If we right-click on the main entity and then open tools, we can move him back to the floor. There we go. That should help him recover more easily. But he does seem a little bit lonely, doesn't he? Maybe now we should go ahead and duplicate him a few times. If we open Tools again and then click on Duplicate Entity, this will open a new dialog window. We'll leave the direction as the default and change the number of instances to 5, spacing each of them by 1 meter. There we go. Now we have 5 bipedal robots in the scene. I think next, maybe we should upgrade him, don't you think? Well, if we right-click in the Explorer pane, you should now see the Replace Materials tool applied to the world appear. I'll go ahead and replace his blue feet with a green material. If we click Execute now, you should see the color of his feet change from blue to green. Finally, if we click on the ellipsis to the right of the physics component, the tool's side menu should now appear. The Apply Force tool will allow us to apply a force to the body's center of mass. We've made some small improvements to configuring signals in the bindings table. When you now go to select an entity from the drop-down, ProtoTwin may automatically go ahead and select the component and property for that signal as well. This is because the beam entity only has a single sensor component, and that sensor only has a single I/O point, being its state property. This improvement should help reduce the amount of time it takes to bind PLC tags to signals in your ProtoTwin models. A small other change we've made is that when you change tab to open the signals table, you can now toggle the value, which should be updated every frame the simulation advances. This is particularly helpful if you want to observe the state of all I/O points in your model, not just those that have been bound to tags. We've also added a brand new robot grounded link component to the application. I'll first go ahead and select the chassis, and then add the new robot grounded link component to that entity. This component can be used to enable robots to be attached to dynamic rigid bodies such as vehicles. In this case, we are specifying that the chassis is the grounded link for the robot. Since the first link of our SO101 robot is based to the chassis, ProtoTwin can't determine what the grounded link is, since there are no joints a part of the robot controller that have a base set to null. This component may also be useful if you have a humanoid robot arm or a 6-axis robot moving along a track, and you don't want the robot controller to solve the link for the track, but would like to drive that link separately instead. Finally, we're pleased to announce the release of ProtoTwin Radiant. ProtoTwin Radiant is our native offline rendering application that can be used to render high-quality realistic videos. But before I show you that, I first need to record a sequence of frames to the GLTF format. You just need to select a desired frame rate from the list of options, hit the button to start recording, and then play the simulation. ProtoTwin will immediately start recording the frames in the background. I'll let the simulation progress for a while so that it can record a few seconds worth of frames. In this example, I've already set up all the materials in ProtoTwin and have added an animation component to the camera entity. The animation component can be used to perform camera movements, which will get exported by the recording. Once you feel like the simulation has recorded enough frames, you can click the Stop Recording button at the bottom to stop the recording, and then save the frames to disk. All right, now that we have ProtoTwin Radiant open, I'll give you a quick tour of the UI. We first need to import the zip file of frames that we saved out for the recording into the tool. You can change the resolution for the recording or select one of our preset resolutions from the drop-down list. It is also possible to import a HDRI environment map into the tool. You just need to click the Import Texture button and then select a HDR file from your local drive. When you're happy with all the options, you can click the Preview button to preview an individual frame. This is quite helpful since it allows you to preview different environment maps and can help you decide whether the options you've selected are good enough for rendering the frames. When you are happy with the preview, you can click the Render Frames button at the bottom left and then click Start Rendering to start rendering the frames. At this point, you just need to wait until Radiant has finished rendering all the frames. You can play the video at any point to preview it, whilst Radiant is in the process of rendering. When the rendering is finished, you can click the Export button at the bottom to export your video to either an MP4 or a WebM file. And that's all there is to it. We hope that ProtoTwin Radiant makes it easy to render extremely high-quality videos of your simulations. We use Radiant internally to render many of our videos, and we're excited to finally offer this powerful tool to our users as well. Rendering high-quality videos can be computationally demanding. It is recommended that you use a machine with a powerful GPU if you want to render more than a few hundred frames. Some videos only take us about an hour to render, whilst others can take a few days. And that's everything. Thanks for watching.